When a massive road roller moves across fresh asphalt, the ground beneath your feet can actually begin to shake. A huge steel drum, weighing anywhere from 8 to 12 tons, slowly moves across the surface, transforming a loose mixture into a smooth, solid road. At first glance, the explanation seems obvious. You might think the machine works simply because it is incredibly heavy. The heavier the roller, the more pressure it should put on the road, and therefore the stronger the road should become. But that is only part of the story. If the roller relied entirely on its static weight, loose stones would simply move away from the pressure instead of locking tightly together, and the air trapped between those particles would remain inside the road. So engineers had to find a completely different solution. The real secret is hidden deep inside that smooth steel drum. Inside the roller is a powerful mechanism that creates thousands of controlled impacts and vibrations every minute. And those vibrations are what truly transform loose stones, gravel, sand, and hot asphalt into a dense and durable road. In this video, we're going inside the road roller to discover how it really works and why its enormous weight is not the main reason roads become so strong.
People walking along the sidewalk can often feel a road roller approaching before they even see it. A deep, low-frequency vibration travels through the ground and into the soles of their shoes. Then they see the enormous steel drum moving slowly across the pavement. Naturally, most people assume that the machine is simply crushing everything beneath it with its tremendous weight. It seems logical. After all, the roller weighs several tons. But the physics of soil and road construction tells a different story. Freshly poured asphalt, crushed granite, gravel, and sand are initially made up of millions of individual particles. These particles have irregular shapes and sharp edges, and between them are countless tiny pockets of trapped air. Those air pockets are one of the biggest problems engineers have to eliminate. If too much air remains inside the road base, heavy trucks and cars will eventually force the loose particles to move. The road begins to settle. Then come the cracks, ruts, depressions, and potholes. In winter, water can enter those tiny gaps. When temperatures fall below freezing, the water expands and pushes the surrounding material apart. Over time, the road begins to break down from the inside. So the real goal isn't simply to push the road downward. The goal is to force the individual particles into the tightest possible arrangement while removing the air trapped between them.
Imagine dropping a massive weight onto a pile of loose stones. The stones don't magically lock together. Instead, they move away from the force, spreading toward areas where there is less resistance. The same basic problem occurs when a heavy roller relies only on static pressure. The machine may compress the uppermost layer, but deeper material can remain loose. The roller moves forward, leaving behind a surface that looks smooth and compact, but underneath, dangerous voids may still exist. Once the machine moves away, the material can partially rebound because of its natural elasticity. The road may look perfect, but beneath the surface, the problem is still waiting. This is why simply making road rollers heavier was never a permanent solution. The engineers needed a force that...
The history of road rollers began with a very simple idea. More weight means more pressure. During the 19th century, some of the first heavy road rollers appeared on city streets. These enormous steam-powered machines looked somewhat like tractors, except their front wheels had been replaced by a massive steel cylinder. Some Victorian-era machines weighed more than 15 tons. They moved slowly, produced thick clouds of black smoke, and filled the streets with the sound of steam escaping from their chimneys. At the time, road crews genuinely believed that massive static weight was the key to building durable roads. But the process was painfully slow. To achieve even a modest level of compaction, operators sometimes had to make 8 to 12 passes over the same section of road. The machines moved at little more than walking speed. Huge amounts of wood and coal were burned simply to move these enormous rollers back and forth. Workers also had to constantly add more gravel as material shifted beneath the drum. And despite all that effort, the results were far from perfect. The upper layer could become heavily compressed while deeper layers remained loose. Engineers tried to solve the problem by making the rollers even heavier, but that created an entirely new problem. Some experimental machines became so heavy that
As cars became more common, roads built using old methods began to deteriorate faster. Engineers were reaching the physical limits of static compaction. No matter how much weight they added, dangerous air pockets could still remain deep inside the road, and those hidden spaces could eventually turn into serious structural failures. You can actually see the consequences today. When an old asphalt road develops a network of tiny, interconnected cracks, it may look like the damage simply appeared on the surface, but often the real problem started much deeper. Loose gravel and poorly compacted material beneath the asphalt slowly shift under the repeated weight of heavy traffic.
From the outside, a modern road roller looks incredibly simple. There is a smooth steel drum. No visible teeth. No blades. No complicated moving parts. But hidden inside that drum is the real engine of compaction. Many people imagine that the drum is filled with concrete or heavy metal to make the machine heavier, but that's not the main secret. Inside the drum is a sophisticated dynamic mechanism. A powerful hydraulic motor receives pressurized oil and uses that energy to rotate a long steel shaft running through the center of the drum. But a perfectly balanced rotating shaft would produce almost no useful vibration, so engineers deliberately created an imbalance. They attached a special weight to the shaft, whose center of gravity is offset from the axis of rotation. This is called an eccentric weight, and it is responsible for creating the powerful vibration that makes modern compaction possible. You can understand the basic idea by thinking about a washing machine.
When the hydraulic motor spins the eccentric shaft at extremely high speed, the offset weight begins rotating inside the steel drum. As the weight moves around its path, it creates a powerful centrifugal force. That force is transferred through the drum and into the ground. The result is not simply pressure. It is a rapid series of powerful vibrations. The roller is no longer just pressing down on the road. It is effectively hammering it. These vibrations can be repeated thousands of times per minute. And that's where the magic happens. Under high-frequency vibration, loose gravel and sand behave differently. The friction between individual particles is temporarily reduced. The stones begin moving and rearranging themselves. Instead of remaining stuck in awkward positions, they shift into tighter configurations. Smaller particles fill gaps between larger ones, and the air trapped inside the structure is pushed out. The result is a much denser road base. The stones become tightly interlocked, and with fewer empty spaces between them, there is far less room for the road to settle later. This is why vibration is so much more effective than simply adding more weight. The static weight pushes down. The vibration helps the material rearrange itself. Together, they create the dense foundation needed for a durable road. But this powerful vibration creates another problem. If the drum is generating thousands of impacts every minute, shouldn't the entire machine shake itself apart? Without protection, the answer would be yes. The constant vibration could damage welds, loosen bolts, and transfer destructive forces throughout the entire machine. So engineers had to find a way to isolate the vibration. The solution is hidden between the vibrating drum and the rest of the machine. Special high-strength rubber isolation mounts act as shock absorbers. The steel drum can vibrate violently, while the main chassis remains relatively stable. The diesel engine and operator's cabin are protected from most of the destructive movement. These seemingly simple rubber components perform an incredibly important job. They allow the machine to generate enormous forces where they are needed, inside the road, while preventing those same forces from destroying the machine itself. So while the drum is violently shaking the ground, the operator may experience only a relatively mild vibration. The machine is essentially directing its energy downward, instead of allowing it to spread throughout the entire chassis.
The operator isn't simply sitting in the cabin and driving back and forth. Modern rollers give the operator direct control over how the machine compacts the surface. With the controls, the operator can adjust the vibration characteristics while the machine is moving. When working with a delicate layer of fresh, hot asphalt, the roller can use faster and gentler vibration. The drum moves frequently, but with smaller amplitudes, helping smooth the soft material without damaging the surface. But when the machine is working over deeper layers of coarse gravel, stronger and deeper vibration can be used. This allows the energy to penetrate further into the road base. Advanced machines can even stop the vibration while continuing to move. Inside some drums, engineers use multiple eccentric weights. By changing the relative position of these internal weights, their forces can either reinforce each other or cancel one another.
Today, road compaction is becoming even more advanced. Modern rollers can use intelligent systems to measure how the ground responds beneath the machine. Sensors inside the vibrating drum monitor the resistance and stiffness of the material with every pass. The machine's computer processes that information and displays the results to the operator in real time. The screen can show a visual map of the area being compacted. As the roller moves across the road, the system can identify areas that are becoming denser and areas that may still require additional work. This means the operator no longer has to rely entirely on experience or guesswork. The machine can help reveal problems that are completely invisible from the surface. A section of road may look perfectly smooth, but beneath it could still be a weak pocket. Intelligent compaction systems help detect these differences and allow crews to focus their efforts exactly where they are needed. With satellite positioning, each section of the road can also be tracked and recorded. The result is a detailed digital record showing where the roller has traveled and how the material responded. The humble road roller has therefore evolved far beyond a simple, heavy machine. What once depended almost entirely on brute force has become a precise combination of weight, vibration, hydraulics, sensors, computers, and real-time.
When a massive road roller moves across fresh asphalt, the ground beneath your feet can actually begin to shake. A huge steel drum, weighing between 8 and 12 tons, slowly rolls across the surface, transforming loose material into a smooth and solid road. At first, the explanation seems obvious. You might think the machine works simply because it is incredibly heavy. The heavier the roller, the more pressure it puts on the road, and the stronger the road should become. But that isn't the real secret. If the roller relied only on its static weight, loose stones would simply move away from the pressure instead of locking tightly together. Worse, the air trapped between those particles would remain deep inside the road. Fresh asphalt, gravel, crushed granite, and sand are made up of millions of individual particles. Between them are countless tiny pockets of air. And those hidden air pockets are one of...
For a long time, engineers believed the answer was simple: make the roller heavier. In the 19th century, massive steam-powered road rollers appeared on city streets. These enormous machines looked like tractors with a giant steel cylinder replacing the front wheels. Some weighed more than 15 tons. They moved incredibly slowly, producing thick clouds of smoke and consuming huge amounts of wood and coal. To achieve even moderate compaction, operators often had to make 8 to 12 passes over the same section of road. But even after all that effort, serious problems remained. The upper layer of gravel could become heavily compressed, while the deeper layers remained loose. Engineers responded by making the machines even heavier. But that approach eventually reached its limits. Super heavy prototypes became so massive that they risked damaging bridges and underground infrastructure. Then, engineers discovered something important. The problem wasn't a lack of weight. The problem was relying on weight alone. Roads needed a force that could reach deeper into the material and make individual particles move and rearrange themselves. That force was vibration. And this discovery completely changed road construction.
From the outside, a modern road roller looks surprisingly simple. There's a smooth steel drum. No visible teeth, no blades, no obvious moving parts. But hidden inside that drum is the real secret. A powerful hydraulic motor spins a steel shaft running through the center of the drum. Attached to that shaft is a specially designed weight whose center of gravity is intentionally offset. This is called an eccentric weight, and it creates the powerful vibration that makes modern compaction possible. Think about a washing machine. When wet clothes gather on one side of the drum, the entire machine can suddenly begin shaking violently. That's because the weight inside is no longer balanced. Engineers took that same basic principle and turned it into a highly controlled construction technology. As the eccentric weight spins at high speed, it creates powerful centrifugal forces. Those forces are transferred through the steel drum and into the road. The roller is no longer simply pressing down. It is effectively hammering the ground thousands of times every minute. Under this rapid vibration, the behavior of loose material changes dramatically. Gravel, sand, and crushed stone begin to move. Particles shift into tighter positions.
But this creates another problem. If the drum is constantly vibrating with enormous force, why doesn't the entire machine shake itself apart? Without protection, it would. The repeated impacts could damage welds, loosen bolts, and transfer destructive forces throughout the machine. So engineers developed special vibration isolation systems. Between the vibrating steel drum and the main chassis are thick blocks made from high-strength rubber and other elastic materials. These components absorb and isolate much of the destructive vibration. The drum can shake violently, while the main chassis remains relatively stable. The diesel engine and operator's cabin are protected from the worst of the movement. This allows the roller to direct its energy where it matters most, into the road. The operator can also adjust how the machine behaves. When working with fresh, hot asphalt, the roller can use faster but gentler vibrations. The smaller movements help smooth the soft surface. When compacting deeper layers of coarse gravel, stronger vibration can be used to push energy deeper into the road base. Some advanced rollers can even stop vibrating while continuing to move. By changing the position of multiple eccentric weights inside the drum, engineers can make their forces reinforce each other or cancel each other out. This allows the machine to switch from powerful compaction to a smooth finishing pass without stopping.
The importance of proper compaction becomes obvious when roads begin to fail. A network of cracks across an old asphalt surface may look like ordinary aging, but sometimes the real problem began years earlier, deep beneath the road. If the gravel foundation was not compacted properly, heavy traffic can slowly move the loose particles. The asphalt above loses support and begins to sink. Eventually, cracks spread across the surface. The same problem can appear around manholes. A large roller drum cannot always reach every narrow area around a metal structure. That can leave behind weak zones where the material is poorly compacted. Eventually, those areas collapse and form potholes. A similar problem occurs where roads meet bridges. The bridge rests on rigid concrete, but the road approaching it may be supported by compacted soil. If that soil remains loose, it can gradually settle under traffic, creating the familiar bump drivers feel before crossing a bridge. Even road edges can become vulnerable. Operators cannot safely drive a massive roller directly over the edge of an embankment. As a result, the outermost section may receive less compaction. Water, freezing temperatures, and repeated traffic eventually exploit this weakness. The lesson is clear. A smooth surface doesn't always mean a strong road. The real quality of a road is determined by what happens beneath the surface, and modern rollers are designed to make sure those hidden weaknesses are eliminated during construction.
Modern road rollers are now becoming far more advanced than the simple machines of the past. Some are equipped with intelligent compaction systems that can actually measure how the ground responds beneath the drum. Sensors monitor the resistance and stiffness of the material with every vibration. A computer inside the cabin processes this information and displays the results to the operator in real time. The screen can show a visual map of the road being compacted. As the machine passes over different sections, the system can identify areas that have reached the desired density and areas that may still require additional passes. This means operators no longer have to rely entirely on experience or guesswork. A section of road may look perfectly smooth from above while still containing a weak pocket underneath. Intelligent systems can help detect these hidden differences.
Satellite positioning can also track exactly where the roller has traveled. Each section of the road can be recorded, creating a digital history of the compaction process. The result is a major transformation in road construction. What began as a giant, heavy machine relying on brute force has evolved into a sophisticated system combining weight, vibration, hydraulics, sensors,
So, the next time you see a giant road roller slowly moving across a construction site, don't assume it's simply crushing the road beneath its enormous weight. The real work is happening where you can't see it. Deep inside the steel drum, an eccentric weight is spinning at incredible speed. Its vibration travels through the drum and deep into the road. Millions of individual particles begin moving. Air is forced out. Gaps disappear, stones lock together, and a loose collection of gravel and sand slowly becomes a dense, solid foundation capable of carrying thousands of vehicles. The most impressive part of the road roller isn't its massive size. It's the invisible force hidden inside that smooth steel drum. Because sometimes, the strongest roads aren't built by using more force. They're built by using the right force in the right way.